Okay, so today we're going to look at general exponential functions. All right, so the motivation here comes from our exponential and the logarithm, which we defined in a previous section. Okay, so here we have a to the r, right? And again, let's follow the reasoning here, right? So we're using the definition and the inverse properties of the exponential and the natural logarithm in order to define just a general exponential of base a, right? So a is bigger than 0. Right now, the reason we need that is if you see the first kind of property that we use is this is the inverse property of how the exponential and the logarithm hold, right? And in order for the natural logarithm to be defined, a must be positive. All right, and then here, now using properties here of the logarithm and the exponents, we can move that here as in front of the natural log of a as a product, r times ln of a. Okay. All right, so now here this will lead us to define the function, right? So that means that we can define our function f of a x equals to a to the x, right? And that means that a to the x, a function of x, is really this exponential, ln of a. All right, and again, that just comes from our inverse properties of the logarithm, right? So any exponential of any base, right? 2 to the x, 2 to the 7 to the x, etc., right? All of that is just a reformulation of an exponential and a natural logarithm. Okay, so that means that since a is really just any positive number, it makes sense that I can put definition to something like this, right? Whereas before, I think we thought of exponents, integer exponents, they had some kind of algebraic meaning, right? 2 squared, 2 to the negative 2, right? We understood what that meant, right? And even rational exponents, 2 to the 3/2, right? Where the numerator was the power, what exponent, and then the denominator was the root, right? That's how we define rational roots, right? But something like this is something we hadn't really discussed, right? But this is nothing but just a value of a natural logarithm. So we can define 2 to the pi as e to the pi ln of 2, which is approximately e to the 2.177, approximately 8.825. Right? So now it has meaning for that exponent to be really any real number, whereas before we kind of we had an understanding of them as simply just rational numbers. But now it's any real number. Right, and then through the derivative, through the laws of the exponential, the natural exponential, that leads us to the laws of exponents that we are familiar with. Right, and again, these all define from the natural logarithm definition. Right, so a to the x plus y is a to the x y, a to the x raised to the y is just multiplication, so it's x times y, right? A to the x minus y equals to a to the x over a to the y, right? And then ab raised to the x is a to the x, b to the x. Okay, so those are just the laws of exponents as previously defined, but here they're derived through the lens of the natural exponential function, which we covered in a previous section. So now, if we have this function here, we're not going to derive the derivative of something like this. Excuse me. The derivative with respect to x of a to the x. Okay, so here using the definition, okay, so I know the derivative of the exponential is just the exponential itself. So we get e to the x ln of a, and then chain rule says to take the derivative. since it's not simply x, right? It's a function of x, of the exponent. The derivative, again, natural log of a is just a constant, right? A is just some real number. It's constant. The variable here is x, so the derivative of x is 1. So we're left with ln of a times e to the x ln of a. But this quantity is just a to the x. So we get ln of a times a to the x. And now we have a new differentiation formula. Right, the derivative of just a general exponential. So let's look at an example here. So an example would be to find the derivative with respect to x of 7 sine x. All right. Okay, so applying the formula that we have above here, where our a is 7, so we natural log 7 and then 7 sine of x. Seeing as this is not just a function of x, applying the chain rule here would be this derivative of sine of x, which is cosine of x. So cleaning this up a little bit, we would get something like that. Okay. All right. Now, in terms of what the graph of a general exponential would look like, right? So here, again, if we have here, f of x is equal to ax, and we know that the f prime of x is natural log a times a to the x. All right, so a is some positive value, right? And x can just be any real number. Right. Now, here, if a is bigger than 1, right, and again, as always here, we make the indication that a is not 1, right? Because that is really just a constant function 1, which we have already rules and properties for that already. So a does not equal to 1. So we'll break it down into two cases, right? If a is bigger than 1, right, here notice that the natural log of any value greater than 1 will be positive, so it'll always be increasing, right? So we get something that looks like this, where it crosses the y-axis at 1. Right, that's when x is 0, right? A to the 0 is 1. Okay. All right. And here we have, right, some properties. The limit as x goes to negative infinity of a to the x, that's 0. And then the limit as x goes to positive infinity of a to the x is positive infinity. Now the other case is when a, and again, this is a to the x, is when a is positive but less than 1. Okay, so that falls between 0 and 1. Now, if you notice the derivative here, any value that falls between 0 and 1 is negative, so that value would be decreasing. So we have decreasing here the whole way through, right? Still crosses at 1. So for this particular case, we have the limit as x goes to negative infinity to be positive infinity of a to the x. All right, again, this is a to the x. And then the limit as x goes to positive infinity of a to the x to be 0. Okay, and then depending on what a is, the steeper or the wider the increase or decrease is. All right, so those are just our graphs of our basic exponentials. Excuse me. All right, so now we'll introduce, now if we know the derivative of a general exponential here, then we can deduce, say, antiderivative formula. Right, so based off of this, now I can define the integral here of a to the x. Right, we do have to account for this constant, right? Remember, natural log of a is just some constant. All right, and the way we account for that, right, is here we're multiplying it. So here in the antiderivative formula, we'll be dividing by it, plus c. Okay, and again, remember, the goal here is that whenever you take the derivative here, right, of this function here, you want it to, of this a to x over ln of a, you want it to be exactly as it is in the, inside the integral. And that does happen, right, because the derivative of a to the x is ln of a over a to the x. The ln of a is reduced, and then we're left with a to the x. So now working through an example here. Right here, let's say we have the integral from 1 to 3 of 5 to the x dx. Okay, applying the formula here, we'll have 5 to the x over natural log of the base, which is 5. And c would be 0 since this is a definite integral. All right, so we'll just leave it at 0. We'll set it equal to 0. And let's say we go from 3 to 1. And then plugging that in, we'll get ln of 5, or excuse me, 1 over ln of 5, 5 cubed minus 5 to the first power, which gives me 120 over ln of 5. Okay, so that is the general exponential function.